So this video is chapter 2 from a chemistry textbook. This chapter also corresponds to modules 1, module 2, and module 7 from my chemistry 1025 notes, as well as my chemistry 1025 videos. So this video is meant to be sort of overview of everything that's in the chapter, the most important highlights. I would encourage you to go ahead and watch the other videos as well if you have any specific questions on any specific topics as well on this material. This image here happens to be an image of a bunch of atoms. We have copper surface which is blue, and the red dots you see happen to be individual atoms which were positioned using an atomic microscope. This particular case, a scanning atomic microscope was used to view the images, view these atoms. So we usually think of atoms as being so small that we can't see them, but there's actually some scientific equipment now you can use to actually visualize individual atoms. Now we can't see the individual particles that make up the atoms, but we can see the overall, the electron environment with which the atoms sort of encompass. An atom is the smallest identifiable unit of an element. And just to review from, I mentioned in the last video, there are 7 naturally occurring diatomic elements. That is H2, N2, O2, F2, Cl2, Br2, and I2. So those are 7 naturally occurring diatomic elements on the periodic table. There are 91 elements which occur naturally, and roughly 20, actually a little more than 20 now elements which are found synthetic. There's actually a total of 118 elements total which have been discovered on the periodic table. So basically, we use something called atomic theory. Atomic theory came from looking at some laws of nature. These are the laws discovered over time. So these laws here, law of conservation of mass, law of definite proportions, and law of multiple proportions. These observations and these laws were used in the development of modern atomic theory. Law of conservation of mass. We attribute this to Antoine Lavoisier. He's known as the father of modern chemistry. And the whole idea here is that if you know the mass of, say, one component, the mass of another component, and you're making a compound from this, basically the sum of the parts equal the total. That's the whole idea here. So if we know how much was used in the reactants, therefore we know how much will be used to make the products. You can't make any more product than what you started with. So you can't have extra mass or missing mass. That just doesn't really happen. At least on using the equipment that we have available to us. So basically the sum of the parts gives us the mass of the total. That's the law of conservation of mass. Basically matter cannot be created or destroyed. Law of definite proportions. This is 1797 by Proust. All samples of a given compound, regardless of the source or how they were prepared, have the same proportions of the constituent elements. So the idea here is that if you decompose, for example, 18 grams of water, that'll break down into 16 grams of oxygen and 2 grams of hydrogen. In other words, 16 over 2 is the same as 8-to-1 ratio. There's an 8-to-1 ratio. So basically, if you had any mass of water, if you broke that down into its components, it will always have a fixed ratio of 8-to-1. Well, multiple proportions. Let's see, we have atoms A and atom B, and they can combine together, and it may, for example, is AB, AB2, AB3, etc. So we have 2 elements, 2 different compounds. The masses of element B that combine with 1 gram element A can be expressed as a ratio of small whole numbers. So we're not going to have fractions. Basically, what we're saying here is the atoms can combine together in whole number ratios only. Here's, for example, let's say we have carbon dioxide, carbon monoxide. The mass of oxygen that combines with 1 gram of carbon is 2.67 grams. So for every 1 gram of carbon, we get 2.67 grams of oxygen. In carbon monoxide, it is 1 gram of carbon gives 1.33 grams. If you were to take this ratio of 2.67, divide that by 1.33, we get a ratio of 2.0. I'm not going to make a too big deal about these different laws here, but these different laws were used in the development by John Dalton to come up with atomic theory. So basically his theory says that all elements are composed of tiny indestructible particles called atoms. Atoms of a given element have the same mass and other properties that distinguish it from other atoms of the other elements. So basically he's saying is all chlorines are the same, all fluorines are the same, all oxygens are the same, but two different atoms are going to do two different properties. But each atom is unique. Atoms combine in simple whole number ratios to form compounds. So again, you can't have fractions. You know, A, B, AB2, AB3, that kind of idea. Atoms of one element cannot change atoms of another element. This is called transmutation. So atoms of lead cannot be turned into atoms of gold. In chemical reactions, the atoms will just rearrange themselves to make new compounds, but you cannot change the identity of an element. So basically his model is 1807. You should be familiar with who John Dalton is and what his model is. So you need to know that this model belongs to John Dalton. So in approximate year is 1807. I'm not going to ask you in what year did Dalton develop his model, but you should at least have an idea who Dalton was and what he did. So his model is called the billiard ball model or the pool ball model. Or it's basically just a marble. So different atoms. So maybe this happens to be an atom for, I don't know, hydrogen. Maybe this happens to be the atom for, some other element. All I'm going to do, all the are spheres with different sizes. So maybe there's a third element, different size spheres, whatever. That's John Dalton's model. It's very simple. You go ahead about 100 years or so, we have J.J. Thomson. He discovered the electron. So basically what he did, he has something called the cathode ray tube. So basically we have a tube here, we take all the air out, so it's under a vacuum. We apply a voltage across these electrical terminals here. And what we generate here is a beam of electrons, which goes from one side to the other. So we have the beam of electrons. And what you found is if you take a magnet, we can actually make this beam be deflected. So basically these electrons being shot across from one side to the other, and from the cathode to the anode, and then basically we use a magnet we can use a magnet to steer these electrons around. It was this principle that was what was used in the old cathode ray tube televisions, the big box TVs you may have seen. There's a big cathode ray tube in the back, which made the picture. And by basically all it was the beam of electrons being steered by a magnet. Let's see. Electrons have negative charge. That's what's important about this. Your electrons have negative charge. J.J. Thomson, he discovered like I already mentioned, he discovered the electron. I was thinking of this guy here. Robert Millikan, he basically took an oil drop. Basically, had some oil in here. He made a mist of oil in this chamber, and as the oil drops began to fall down, he was able to use the electrical charged plates to make the drop be suspended, and he was able to develop what's known as the charge to the mass ratio of the electron. So that's what Millikan did, his oil drop experiment. He discovered the charge of the electron and its charge to the mass ratio. That's Millikan. This is Thomson's model. We call it the plum pudding model. So, or imagine like pudding or gelatin. Inside the jello, inside this pudding, we have plums. The plums became known as basically the electrons, and the jello or the pudding is going to be just an area of this positive charge. So I got positive charge here, and I got negative charge electrons, and that's it. That's basically his model. 1909, we have Ernest Rutherford. What he did was called the gold foil experiment. His apparatus kind of like this here. We have a gold foil, which is really, really thin. Over here we have a source of radiation called alpha particles, alpha radiation. He sent this radiation to the foil, and what we found was that most of it can't pass through the foil and was detected on the opposite side. Here we have a screen, a detector screen, which within basically lit up or give off light when these alpha particles pass through and they hit the screen. Most of the light occurred on the opposite side. Some of the some of the blips occur at at some angle, some angle away from the center, and occasionally, very infrequently, you notice a blip over here, or maybe one came back this way, for example, where the angle was very extreme. Basically, it hit and bounced back off. So basically, it almost came back towards its source. But basically, what the discovery of this was is that when they bounced back at you, or back at the source, they had to hit something very dense. What the dense thing that they found was turned out to be the nucleus. Now, it turns out most atoms happen to be empty space. Atoms are mostly empty space, which is why most of these alpha particles shot straight through, basically essentially uninterrupted. But occasionally it would strike the nucleus and bounce back. So his conclusion with the nucleus had to be very dense. Now this particular picture shows protons and neutrons, and he did not know that. He did not know anything about neutrons at the time, but that's where these particles are actually located. They're located in the nucleus. So basically we have most of the atom's mass and all of its positive charge in the core are called the nucleus. Most of the volume of the atom is empty space, where the negative charge is distributed around this empty space. And there are many negatively charged electrons outside the nucleus that are positively charged, as there are positively charged particles. Sorry, there are as many as, so the same number of protons as electrons. So the atom is electrically neutral. So the sum of the positive charges equal the sum of the negative charges. Now, neutrons were the last particle to be discovered. They were discovered by Chadwick in the 1930s. Now, neutrons having no charge is what made them more difficult to be discovered. What they're finding is that atoms had less mass than what was anticipated. So they measure something, you find the mass found the atom had a certain weight to it, or a certain mass to it, but it didn't match what was with theoretical calculations. The mass was missing. And so it turns out this missing mass came from the particles which had no charge. They became known as the neutrons. Protons and neutrons have essentially the same weight, or the same mass, but neutrons are ever so slightly heavier. So basically up to this point we have the nuclear model of the atom. The nuclear model atom is just going to be protons in the nucleus, electrons on the outside. The electrons didn't have any particular confinement. So you can imagine the electrons flying about, around this nucleus in any random way. And what we know is that electrons are neutral or negative charge. Protons are positive charge. So as these electrons, as they moved around the nucleus, we know opposites attract. So what should happen in time, this electron should eventually crash into the nucleus. So you can imagine all the electrons on the outside of the nucleus eventually all crashing into the nucleus itself. So matter should be self-annihilating. Well, that wasn't really occurring. Matter wasn't just destroying itself. So the reason was, now, why? Well, Niels Bohr, this is 1913, he developed what's known as the Bohr model of the atom. And this is the model of the atom where we have the protons and neutrons in the nucleus, and we have electrons which are confined to these energy levels. So this picture here shows energy levels, these circles, around a nucleus. So so in this particular picture, neutrons are not indicated, it's just the protons. So we have 1 proton, 2 protons, 3 protons, 4, 5, etc. This is for the first 20 elements of the periodic table. The rings here show the number of electrons which can go in these rings, or in these energy levels. So hydrogen has 1 ring, or 1 energy level. Helium's got 1 energy level. And the first energy level holds a maximum of 2 electrons. Now we get the next period of the periodic table down, this next row down. You have lithium, beryllium. Keep going to your right, you find boron, carbon, nitrogen, oxygen, fluorine, and neon. Notice these all have 2 rings. The first ring, or first energy level, has a maximum of 2 electrons, and I'm adding 1 more electron all the way from left to right. Now the electrons in the last ring, they're called the valence electrons. The electrons interior inside the valence electrons are just called the core electrons. And again, as I go left to right, I'm adding one more electron to the last ring, or I'm adding one more valence electron. So neon's got 8 valence electrons, fluorine's got 7 valence electrons, oxygen's got 6 valence electrons. Next row down, we have sodium all the way across. Same idea, the pattern just repeats. The first 2 rings are full. I'm adding one more electron to the last ring. And then I end up with calcium at the end over here. Once I pass calcium, as you might recall from Chemistry 1025, the pattern now changes. This is something that was addressed in Module 12 of Chem 1025, and we'll address this again in, I believe, Chapter 7 and Chapter 8. But this shows how you diagram the first 20 elements based upon Bohr's model. Now realize that the neutrons were left off. Okay, I did not include the neutrons in this particular chart, but they would also be the nucleus as well. So I'm only showing the protons and I'm showing the electrons. And these are, of course, for neutral atoms. So this is a quick summary of different particles. Notice that protons and neutrons have essentially the same mass, 1.67 to the negative 27 kilograms. If you look at electrons, they're much lighter in mass, right? 0.00091, so they're, tens, hundreds, thousands, they're 10,000 times smaller in mass, essentially. Here's the same mass in terms of what are called atomic mass units. So neutrons of 1.008 versus protons of 1.007 atomic mass units. Electrons of 0.0005, so you can see it's much smaller. You don't need to memorize these numbers, by the way. You should know the charges. Protons have positive charge, electrons are negative charge, neutrons are zero charge. And notice the charge in coulombs. This is partially discovered by Millikan, have opposite charges for protons and electrons. But it's most important in this class to understand what the charges are and how that relates. Now, when it comes to the atoms, we should be able to diagram them. So the number of protons defines the element. So if you change the number of protons, you can change what the element is. So for example, carbon's got 6 protons. Oxygen has got 8 protons. So every element has a different number of protons. That determines what the element is. That defines the element. The number of protons is oftentimes given the symbol Z to represent the positive charge of the nucleus. So for example, if Z is equal to 6, we're talking about carbon. If Z is equal to 8, we're talking about oxygen. So the number of protons is defined by the symbol Z. On the periodic table, the atomic number is written, usually written above the element symbol. So boron's got 5 protons, chromium's got 24 protons, tungsten's got 74 protons. That is the atomic number. Every element has its own atomic symbol. Now, when it comes to different atoms, you may have heard of things like, for example, carbon-12, carbon-12, or 12C. So this is these is also carbon-13, 13C, and 14C. These are called isotopes, and that deals with the number. And so basically, these are all 3 different versions of carbon, but each carbon has a different number of neutrons. So there's another number called the mass number, which is important. Now this number is not on the periodic table. Okay, it's not on the periodic table. The mass number is the number of protons plus neutrons, and it has to be a whole number. Okay, so on the periodic table, usually written below the element symbol, it's not in this table, but usually written below the symbol, you might see some other numbers. For example, carbon might say 12.011 or something like that. That number you see there is called the average atomic weight. But that is not the mass number. Now these 3 different versions of carbon are called isotopes. The only difference is the number of neutrons. So in element simple notation, an upper left corner, that's going to be the mass number. The bottom left corner, that's going to be the atomic number. All these have 6 protons. So how many neutrons do these all have? If you subtract these numbers here, that'll tell us the number of neutrons each of these isotopes have. 12 minus 6 is 6, 13 minus 6 is 7, and 14 minus 6 is 8. So carbon 12 has got 6 protons, 6 neutrons. Carbon 13 has got 6 protons, 7 neutrons. Carbon 14 has got 6 protons, 8 neutrons. They're called isotopes, and pretty much every element is going to have isotopes. Actually, they all have isotopes. Some isotopes are stable, and other isotopes are radioactive. It's the fact that we have these different isotopes in different abundances in nature is going to determine the average weight of a given atom. So basically, knowing something about the percentages gives us natural abundance and so on. So I'm going to talk about this a little bit later. This is the notation I was talking about a second ago. We have mass number upper left. Sometimes mass number is given the symbol A. Remember, that's protons plus neutrons. The symbol Z, that was atomic number. That's the positive charge of the nucleus. And the element symbol to the right of all that. So here again, we have 3 isotopes of neon. Neon 20, neon 21, and neon 22. But since they're all neon, they've all got 10 protons. And that gives us basically, so is the symbol notation. Now you might see something like this sometimes. Maybe you get, maybe it says Ca positive 2, and maybe it says 40, and maybe it says 20, something like that. Same idea. I have a mass number of 40, atomic number of 20. In this case here I put a charge in. So if the particular element happens to be an ion, whether it be positive or negative, the charge will be written in the upper right-hand corner. If the element is neutral with no charge, there will be no charge to be written. Sometimes the mass number is also written to the right. So neon 22 could be written this way, or neon 22 could have been written, this other way. So you have to be familiar with that. This happens to be the percent abundances of all these. Mass numbers are given, the percent abundances. So the overall average weight of neon is going to be closer to neon 20. So the atomic average weight of neon is going to be close to 20 or thereabouts. It'll be a little bit over 20 because the other isotopes are above 20. They have some percentages above 20, right? We have a small amount of neon 21, and we have a little over 9% happens to be neon 22. And so its overall weight is going to be close to 20, however. So I'm going to show you how to do a calculation involving this in the later slide. So basically, all elements on the periodic table are neutral. If an atom happens to lose electrons, for example, if sodium, with its 11 electrons, if that happened to lose an electron, we're going to end up with Na positive. That's called the sodium cation. So if you lose electrons, you become positive charge. If you gain electrons, you become negative charge. So fluorine, with 9 electrons and 9 protons. Sodium, by the way, had 11 protons as well. If you were to gain an electron, you can become F minus or F minus 1 with 10 electrons and 9 protons. So you have to remember here, if you lose electrons, the number of electrons are going to go down. In this case, it's 10 electrons. Protons aren't going to change. Alright, sodium is still going to contain 11 protons in either case. Fluorines have 9 protons in either case. It's the number of electrons which are going to change. So if you have more protons than electrons, you can be positive charge. And if you have more electrons than protons, you have negative charge. So this shows here basically the common charges you need to know. You need to know these. So all of group 1 here, all of column 1, or 1A, they're naturally going to want to form a positive 1 charge. Group 2 here, they're all going to want to form a positive 2 charge. They're not going to be any exception to this. So plus 1, group is plus 1, they're plus 2. Group 3 down here, they're going to tend to form a positive 3 charge. Now the idea here is they're all trying to look like a noble gas. So the group 8 elements have a full number of valence electrons. So if you take an electron away from sodium, if sodium lost an electron, it would have a similar electron arrangement compared to neon. Neon's right here. If you take one away from sodium, it's going to look like neon. If we took one electron away from potassium, it's going to look like argon. Argon came down here. So the idea is if elements which lose electrons are trying to look like noble gases, that's group 8. The nonmetals on the right, if they acquire electrons, they look like group 8. That's the whole idea in chemical bonding. We're trying to look like a noble gas, because the noble gases are known to be stable. So group 5, notice it is 1, 2, 3 blocks away from a noble gas from group 8, so it's going to be -3. It wants to acquire 3 electrons. Group 6 is 1, 2 away, so it's -2. Group 7 is 1 away, so it's -1. I also going to throw in 2 more elements here. We have zinc, Zn +2, and Ag +1. Yeah, you need to know those as well. I'll talk more about this in the next chapter. But you need to know this chart. You need to memorize this. Group 1 is +1, Group 2 is +2, Group 3 is +3, Group 5 is -3, Group 6 is -2, Group 7 is -1. Hopefully you know this from last semester. Alright, so the periodic table is organized based upon repeating properties. The first periodic table, which was organized based upon properties, was made by Dmitry Mendeleev in 1869. So basically, in vertical columns, elements each column have very similar properties, similar reactivity. Alright, so I'm going to skip through these slides here. You can read these on your own. Metals, nonmetals, metalloids, and so on. Main group elements are going to be what we see, in group 1, group 2, and then 3 over. The transition elements are going to be in the middle. And we have a staircase here. The elements on the staircase are going to be known as the metalloids. Okay, they're going to be known as the metalloids. The ones on the staircase, usually above or below, are the metalloids. So aluminum is clearly a metal, but boron's a metalloid, silicon's a metalloid, germanium is a metalloid, and so on. They're called metalloids. They're kind of like in between metals and nonmetals. Metals tend to be shiny. They tend to form positive charge. They're ductile. They can stretch them. You can shape them. You can bend them. Nonmetals on the right tend to be dull. So they could be gases or liquids. They could be they don't conduct electricity, and so on. Metalloids have properties sort of in the middle of them. Again, you can read this all on your own. You can read this on your own as well too. Again, you can read that. I'll let you guys read through all this. I may ask you in the test, what are the alkaline, what elements make up alkali metals, which elements make up alkaline earth metals, etc. You should be familiar with those kinds of questions, but I'm not going to go over this in detail. Again, same slide as before. You need to know what charged ions are going to form. Alright, so when it comes to the periodic table, you're going to find underneath each element symbol a number, which tells us something about its size. That's known as the average atomic weight. Now, the atomic mass of each element is directly beneath the element symbol of the periodic table, but is not the same as the mass number. It may be similar to the mass number, but it's not the same. This average atomic weight is the weighted average based upon the natural abundance of each isotope. So this is called the mass spectrometer. You got our sample. Basically, we're going to send it through this chamber. We're going to ionize it, send it through a magnetic field, and basically this magnetic field is going to cause these particles or charged ions or whatever to be deflected and be detected on the screen. Depending upon its charge and its weight, it will determine where it lands on the screen. So the heavier particles tend to go more of a straighter path because they got more momentum, they're not going to bend as easily. The lighter particles are going to be more influenced by the magnetic field, and they're going to be bent at a steeper angle and be detected further down, or at least more to the left in this diagram. And basically by counting the number of particles they hit different spots, so we can count how often a spot hits here, a spot hits here, how a spot hits here, and by knowing how its mass is related to its distance on the screen, we now can make a histogram of its abundance and so on. So basically we can plot. We got this, and we got this, and maybe we got this. So we have higher abundance here, and maybe we have lower abundance maybe over here, and smaller abundance maybe on this side. So this isotope here would have the greatest contribution towards the average weight, towards the atomic weight of an element, simply because it's got more abundance, higher in the scale. So look at the example here. Naturally occurring chlorine consists of 75.77% chlorine, mass number 35, so that's 35 Cl. We've got, and it has a mass of 34.97 atomic mass units, close to 35. It's 24.23% chlorine 37, so that's 37 Cl, that's the mass number. Its mass is 36.97 atomic mass units. So what we do, we convert these percentages into decimal form. So 24.23% becomes 0.2423. We're going to multiply it by its mass, 36.97. Get a number for that. Do the same thing with the chlorine 35 isotope, 0.7577, multiply that by 34.97. Get a number for that, and add them up. So I get a weighted average of 35.45 AMU. This happens to be the number we find on the periodic table, 35.45 AMU, or atomic mass units. Now you might be familiar with the terms grams per mole. So it's going to be the same. What you're going to find out is that AMU per atom is the same thing as grams per mole. They're going to have exactly the same units, the same number for that. So basically this is chlorine 35. Notice that this is what's on the periodic table, what we just calculated. We can do this for any element you want. All we need is enough terms to represent, so the sum here, this means sum. So the chlorine example only had two terms. We had chlorine 35 and chlorine 37. We only needed two terms. But if you got three or four isotopes, we simply build in more, make this longer. So basically, we can find the average atomic weight of any element you want using this technique. So this is why average. So this is why it's called an average. It's the average. It's a weighted average of all the elements in nature a particular element has. So basically, we're going to use this weighted average to do counting. You'll find this in Module 7 of in the Chemistry 1025 Survival Guide. So basically, since if I have a given bunch of atoms, we have this. You'll have an average weight. Okay, so for example, this atom could be, for example, chlorine 30. It could be from chlorine 35. This one could have been from 37. You don't really know, but on average, it weighs 35.45. Let's say we're talking about individual atoms of chlorine. So we're going to use this weighted average to do calculations. That's where moles come into play. So a mole is like a chemist's dozen. So just like 12 occurs, use 1 dozen is 12. A gross is 144. A mole is just Avogadro's number, 6.022 times 10 to the 23. That's Avogadro's number. So that's how a mole is related. Again, hopefully you've seen this last semester in Chem 1025. Now, basically, the way a mole is defined is related to carbon-12. So carbon-12 is defined to be exactly 12 AMU. So carbon-12 is defined to be, or in other words, 12 grams of pure carbon-12 is basically giving me the reference for where this number came from. You don't really need to know that, but it's just an interesting little tidbit of information. Okay. So 1 mole atoms, that's equivalent to 6.022 times 10 to the 23 atoms, or 6.022 times 10 to the 23 atoms is equivalent to 1 mole of atoms. So basically we can use this conversion to convert between atoms and moles. We can also use the average atomic weight to convert between grams and moles. And we can use the average atomic weight and the conversion between moles and atoms to find atoms. So basically you need to think a look at a problem and think about what is needed to solve the problem. So let's see. Let me jump ahead a little bit here. So yeah, this is what I mentioned. So in case of carbon, 12.01 grams is equal to a mole of carbon. This is what I'm saying. We can use the average atomic weight in the periodic table to relate that to moles. We have it's easier to do some questions and some problems directly. Alright, so let's look at some example problems involving this. So let's say we're given 150.0 grams of, let's do individual atoms. Let's say we're talking about aluminum. I want to convert that to moles. So if you look at the periodic table, it's atomic number 13. Aluminum has an average atomic weight of 26.98. So Al is 26.98 grams of Al. Now, aluminum. Now, when you look at the periodic table, I'm always going to keep two decimal places here. If you want to take more than that, that's up you can, but I'm going to stick with 2. If I want to convert this to moles, this means 26.98 grams per mole. So 150.00 grams of Al. If you say, well, 1 mole of Al, that's equivalent to 26.98 grams. We do the math here, that'll tell us how many moles we have of aluminum. 150, divide that by 26.98. Now we check significant figures here. This number here, 150.00, it's got 1, 2, 3, 4, 5 sig figs. Therefore my answer gets 5 sig figs. So we have 5.55, that's 3 sig figs. 9, that's 4 sig figs. 6, 7, that's too many, but so it's 1, 2, 3, 4, 5, that's 6 sig figs. Number 6 shows the fifth one. Look to your right. That number's 5 or larger, so we get 5.5597 moles of aluminum. This is how we're always going to show our work. If we're given grams, want to find moles, we divide it by the average atomic weight to give us the number of moles of that element. Let's try another example. Let's see we're given moles and want to find grams. So let's say we have 0.750 moles of sodium. I want to find grams of sodium. So this is just a backwards problem, starting with 0.750 moles of Na. Well, the periodic table says that sodium is 22.99 grams of Na. That's grams per mole. If I want moles to cancel, I put moles on the bottom. So it's 22.99 grams to 1 mole of Na. Notice moles, whoopsie, what did I do wrong? I wasn't paying attention. 1 mole of Na is 22.99 grams. So if you ever want to know what comes next, look at the previous step, moles on top, means moles go on the bottom. Check units. So moles cancel, moles cancel. Now how many sig figs this time? 1, 2, 3 sig figs. Therefore I want 3 sig figs on the answer as well. So 0.75 times 22.99, that is equal to 17.24. That's good. So that's too many sig figs. Check them. 1, 2, 3. Look to your right. That number is less than 5, so we get 17.2. 17.2 grams of Na. So that's how we go from moles back to grams. Now, how does Avogadro's number come into play with this? What if you want to convert, for example, moles to atoms? So maybe we've got 0.6200 moles of Na. I want to convert this to atoms of Na. Do I need the atomic weight of sodium? No. Because I'm going from moles to atoms, I'm not going in the grams at all. So we have 0.62300 moles of Na. Well, now we use Avogadro's number. 1 mole of Na. Notice moles have to go on the bottom because I have moles on top, right? I have moles here, means I need moles here. Number on top has to be Avogadro's number. 6.022 times 10 to the 23rd atoms of Na. How many sig figs? Well, 1, 2, 3, 4, 5. These trailing zeros are after a non-zero digit, they're after the 3, and they're at the decimal place. So we count them. It's 5 sig figs. 5 sig figs. So 0.623 times 6.022 times 10 to the 23rd. The 5 sig figs now, it's 3.75. That's 3 sig figs. 1, that's 4 sig figs. 7, that's 5 sig figs. The next digit is 0. So I'm not going to do anything else. Don't forget times 10 to the 23 power. Atoms of sodium. That's how we solve that one. Now, what if you want to somehow include grams with all this? What if we're given 17.84 grams of Na? I want to convert this into atoms of Na. So this is a combination the problem we just did in the earlier question. There is no direct conversion from grams to atoms. You have to go to moles first. So we're going to go to moles to atoms. 17.84 grams Na. Again, sodium is 22.99 grams per 1 mole of Na. Check units. Again, my assumption is you know how to find this information from Chem 1025. If you don't, please refer to my Module 7 video from my Chem 1025 notes. Now that gets us moles of sodium. 1 mole of Na is 6.022 times 10 to the 23 Na atoms. So the moles cancel. So it'd be 17.84. Now 17.84 has got 4 sig figs. (17.84) divide 22.99 times 6.022 times 1023 equals the 4 sig figs. That is 4.673 times 10 to the 23rd power. So 4.673 times 10 to the 23rd. It's a little real space over there. But that's how you solve that problem there. So with 2 steps, going from grams to atoms, we need to put the atomic weight in the middle. So this is a brief review of how to do some of these mole problems. Again, I have much more details of this in my Chem 1025 videos. So if you don't remember how to do this from Intro to Chem, please go back and watch those videos for more information.